Hello, today we will be looking at the design and finite element analysis of a chevron brace connection. So for this problem, we are to design the chevron brace connection using AISC 14th edition LRFD for designed steel sections and design loads shown in the table. Specifically, we are determining the following. First, the design, dimensions, and thickness of the gusset plate, assuming an A36 plate, the sizes of the fillet weld required using E70 electrode, and lastly to determine if beam web doubler plate is required. So for this particular connection, we will be using a W18 by 50 beam, wide flange beam. The braces are connected to the beam via a gusset plate with an unidentified length and depth with an assumed thickness of 5/8 inches, and the HSS brace has our HSS 7 by 7 by 1/2 vertical braces. So the braces are also under 180 kips of tension. One brace is in tension, one brace is in compression. While the angle in between the y-axis or the vertical at the working point and the axis of the brace is equal to 42 degrees. So applying the calculations as necessary, the design assumptions are the design summary is as follows. The gusset brace connection, we will be using a 12-inch by 40-inch gusset plate with a thickness of 5/8 inch and a 7-inch long 5/16 inch thick fillet weld on both sides. And for the brace to beam connection, to connect the gusset to the beam, we'll be using 1/4 inch fillet weld on both sides, and we will not require a web doubler plate. So now we will be looking at the finite element analysis. For this particular analysis, we will be using the program Ansys. Here we have our model for the finite element analysis using Ansys. So this is our meshed section. For this, we assume that the beam is fixed on both ends. The, the all of the elements are modeled together as a singular entity. Thus, they have the same color gradient among all four elements. We also assume that one brace again is in tension, one brace is acting in compression. So now we will look at the meshing and make sure that the model is compatible. So finite element analysis requires that the interface between the elements, the different elements, are connected by the node, or that the nodes between the elements are coincidental. So as you can see here, the nodes along the edge of the beam flange, and the gusset plate are coincidental. So this means that the nodes will allow for proper transfer of forces. So this looks good. This is exactly how we expect it to be, and it will behave the way we expect it to be. The same goes for the connection between the gusset plate and the brace. As you can see, the nodes are coincidental on all sides. And so this should facilitate a more accurate depiction of the model. So now we will look at the total deformation of the model to see that it is behaving as expected. So as you can see here, it is behaving as expected. We have compression here, so this portion of the beam goes up. This portion is in tension because of this brace, and it goes down. And it looks like our model is performing the way I expect it to be. So now we will look at the equivalent stresses, or the von Mises stresses. So taking the forces along, or the stresses along this section, we have these values, and if we average these values, it will be somewhere around 20 to 21, 20 to 21 KSI. We will compare this with the value that we obtained from the Whitmore section from our mathematical computations. and the gusset stresses based on AIS specification J43, the shear is equal to 21.6 KSI, which is very close to the values shown here. And so this looks like, and this we can say that the model is closely following the mathematical stresses or the mathematical model. So maximum principal stresses are as follows. For the beam stresses are the transverse shear along the beam web. The stresses are somewhere around 15 KSI. Maximal principal stresses along the gusset somewhere between 25 to 9, so that's somewhere around 17. And along this section, it is averaging at around 8, around 6 KSI. Also, it is worthwhile to note that the most stressed section are at joints or the points of connection, smaller points of connection, particularly here and here and here, which is how we expect our model to behave. Same for the equivalent stresses. We also have max stress occurring at the corner points. So that concludes my report for final element analysis. Thank you for listening.